go ahead and get started. I've titled my presentation here "Seeing is Believing" because I think that's kind of what I'm hoping that everyone can take away here is that what in situ allows you to do is explore materials in sort of unprecedented manner so that you can actually see what's going on, witness firsthand some of the reactions and dynamics that are occurring at the nanoscale. But first off, just to start, I always like getting a sort of a background of folks who may be familiar with TEM, maybe not. So as you may know, TEM was first sort of conceived in the early 1940s. Ernst Ruska won the Nobel Prize for the discovery and the development of the transmission electron microscope. And what I'm showing here is just sort of a high-level overview of something I think anyone who's familiar with TEM is kind of sort of familiar with just from an outside perspective, which is that this technique has grown and being increasingly adopted by researchers around the world, and that shows up in the publication record. So if you go to Google Scholar and you just look at TEM, on a log, and you plot that on a log scale, this is kind of what you'll see. Over time, the transmission electron microscope has evolved from just a simple high-resolution imaging tool to a really, really rich characterization tool set that allows you to study things like defects and dislocations in your material, stacking faults, but also to characterize it electronically through EELs and other techniques like that, and also chemically through things like EDS. So the technique has grown quite a bit over the years. And I always like putting this up here just to sort of show some of the developments that have really boosted the capabilities of this tool. Recently, spherical aberration correctors have allowed us to image at much higher resolutions than previously possible. Direct detection cameras have allowed us to do things at really, really high signal-to-noise ratio. And these are just increasingly sort of growing the number of publications and the active utilization of this tool. One of the other reasons I put this up here is that it shows something that a lot of folks aren't familiar with, which is that the first in situ publications and the first results that we would classify as in situ were actually back in the 1940s. So some of Ernst Ruska's very first publications, some of his very first research characterization sort of problems that he was addressing actually were a breed of what we would call environmental transmission electron microscopy. Now, we haven't really seen a lot of utilization of that capability over the several past decades sort of following this. And I'll talk about that in a bit, but before I get into that in too much detail, I always like explaining what it is that I mean when I say in situ. So again, if you're familiar with TEM, you're familiar with some of the things that you can do with that tool. So I always like thinking about these microscopes as their potential on a characterization axis. So at TEM, you can do a certain amount of things. With TEM, you can do quite a bit more in a lot of cases. But in general, you're characterizing your sample in a static environment. So whether that's you're characterizing its chemical makeup, whether you're characterizing its crystallographic makeup, or you're just characterizing size distribution. These are all things that are accessible to you while you're running the microscope. Now, in situ, you're transforming the characterization axis into this experimental space. So now, not only are you characterizing your sample using any one of the tool sets available to you, but you're also characterizing that as a function of some sort of experimental parameter. So whether that's adding some sort of stimuli, mechanical, electrical, thermal, or imaging in a liquid environment, you now have the ability to go into this experimental space, really improving the richness of your data set. And of course, in situ, because you're doing all of this stuff as a function of experimental space, you can also start looking at things as a function of time. So what you're actually witnessing here is a catalyst sample that's actively undergoing oxidation and reduction within the microscope. And this is the kind of results that you can see that researchers are routinely seeing in the microscope when they're building in situ into their portfolio. Right? So you're not just imaging in a static environment, you're witnessing real reactions occurring in real time at the nanoscale. So this is sort of what in situ allows you to do is transform what's simply a characterization tool into a really, really rich data set, allowing you to understand your sample in more detail. Now, when I always started at Protochips, one of the things I was curious about is like why isn't anyone using this? Why is this not the standard way of doing it? Essentially, you're taking all of the stuff you can do on a benchtop and you're just putting it in a microscope so you can resolve things down to atomic resolution. And it turns out that in the early days, a lot of people actually were using this. If you think about a microscope, there's really no reason why you wouldn't want to start seeing things sort of moving. Like if you're imaging a cell in an optical microscope, you want to see how it's interacting with its environment. But that's not the case for TEM. And the reason why is because in the early days, although there was a lot of interest, there were just too many variables in the TEM that really inhibited this technique. And you actually see this in a review paper in the 1970s, which basically said that in situ was tedious, it was finicky, it was unreliable, and most importantly, and the most problematic, it was irreproducible. And as you know, reproducibility is sort of the pillar of scientific requirements. So as a result, no one really used this technique, or just wasn't adopted as much. All of this changed in the late 2000s with the advent of MEMS-based sample control. So this turned what was otherwise an inert, unreactive substrate into an active participant in your experiment that allowed you to manipulate, control, and otherwise characterize your sample as a function of these different environments in real time. And so since then, we've seen a huge growth in the number of folks who are turning to these types of techniques to characterize their samples. So this is, again, just you look at Google Scholar, look at how many people are doing in situ as a function of TEM. This is kind of what you'll see. So there's been a tremendous growth recently, and Protochips has been at the forefront of a lot of that development through some of the capabilities in our tools, which I'll show in a bit. But really, I think this is cool and all to see that the scientific relevance has grown over time. But I think sort of in a nutshell, this is the reason why a lot of researchers are starting to turn to these techniques more and more. So this is a very, very, very small subset of all of the publications that customers of ours have produced from scientific disciplines spanning the entire scientific discipline. So this is liquid cell, gas cell, heating, biasing is just some video sets. The reason I show this, though, is just to give you a sense of the really rich data sets, the really rich dynamics that you can characterize in situ in the microscope. So that's my general 20,000-foot overview of in situ. But the way my talk will occur today is actually I'm going to go through our three products. So as you can probably tell, I don't usually like talking about the product features and the specifications or anything like that. What I'm instead going to do is I'm going to talk about what people have actually done with our products and actually show you science and show you results. If you want a chair, you've got an extra one here.
Thank you.
Yeah, I don't think I need to stand or I'll sit. So yeah, this is the way my talk will go. Is I'll kind of go through each of our three products, explain how they work. I'll explain some of the things that you can do with them. But in general, I'm going to focus on the applications. But I do like putting this up here as just sort of a high-level overview of what these systems do. So we have three products. One is a gas cell that also does heating. Today we'll actually see the fusion, heating, and electrical system. And we also have a liquid cell that can do electrochemistry and liquid heating. I also put this up because no matter where you fall in the realm of science, it's very likely that one of these products is relevant to you in some way. So I always like putting up a huge, broad array of applications, but I also like pointing out that a single application can be served by multiple products. So for example, if you're doing batteries, if you want to study them in solid state, you can look at them in fusion. If you want to study them with a liquid electrolyte, you can look at that in a liquid cell. So we build these products to work together. We build them to access a pretty wide array of research disciplines. So what I'm going to do is kind of go through these in three parts. I'm going to go through each of the three products and talk about them, starting with our fusion system. So we call it fusion because it can do two things and do them simultaneously. That's heat your sample and also apply some sort of electrical stimuli, and you can also do that at the same time. Everything that we've done here is fully approved and endorsed and actually sold by Thermo Fisher and Joule. So we don't let these systems hit the market unless they're comfortable with them going into microscopes. But yeah, the pumping control in general is really good at handling degassed materials.
Thank you.
Yeah, no problem. So going through how these systems work, again, I like explaining how they work before we actually go into what they do. This is just kind of an overview if you're not familiar with this sort of configuration. So in all cases, you're going to be depositing your sample onto a MEMS-based sample support. We call them e-chips. That's what I'll call them from now on. On that e-chip is patterned electrical electrodes for a wide variety of different characterization sort of protocols here. That e-chip is then just loaded directly into the holder. There's some contacts that come down. To change the experiment, you just change the chip out. So if you want to do electrical biasing, we sell chips for that. If you want to do thermal control, we have chips for that. And we have different permutations of all of these. And then once you've loaded your sample onto the chip, it goes directly into the microscope just like any other holder would. Once within the microscope, your sample is sitting between the two pole pieces, so you're able to image your sample. And then this is just kind of showing some of the things that you can do with it. So you can heat your sample up to 1200 degrees with our thermal system. You can go up to 1000 degrees per millisecond, so very, very fast heating and quenching rates. And it's also thermally uniform, which I'll show in a bit. So that's heating your sample up. On the electrical biasing side, you can apply picoamp electrical stimuli. You can go higher than that if you want. You can resolve to very, very fine, even in the femtoamp regime, you can resolve the sort of currents that are flowing through. And then you can also do both of those simultaneously. So if you want to do 4-point probe electrical measurements at really high temperature, you can also do that. So that's why we call it fusion, right? So we do all these things. Our beta tilt control is actually pretty unique in that the electrical contacts stay in intimate contact with the chip at all times. So regardless of what you're tilting it out, in beta there's no fluctuations in thermal or electrical capabilities. This is showing in cross-section here that you can resolve EES. So you have direct line of sight to the EES detectors, whether you've got side entry or sort of the quad-X system. Let me get you it. Do we have chairs for everyone? All right, cool. If there needs to be an extra chair, I've got one. Yeah, so that's sort of the overview of the system. So as I mentioned, I'm not going to talk too much about like the specific features, the specifications of the product, but what I will do is show you what you can do with it. So this is the first application I'm going to show, which is in the characterization of metallic glasses, specifically looking at the onset of crystallization. So as you probably know, there's a lot of really fundamental science that's still to be understood in the field of crystallization. So whether you're looking at phase change materials that are going back and forth between a glassy and a crystalline state, or if you're just studying metallic glasses, which tend to be thermally unstable, there's still a lot that's not really well understood about how the crystallization mechanism occurs on the nanoscale. So these particular researchers were studying a subset of glasses which were actually nanowires. So they were nanowires, but they were also glassy, and they were using that as an analog to understand more broadly the crystallization mechanisms occurring on the nanoscale. So in order to do that, though, they needed very, very accurate, precise temperature measurements. As you'll see in a bit, what they essentially wanted to do is sort of mimic DTA or DSC, some of these calorimetric measurements, so they could very specifically and very accurately characterize the onset temperature of these crystallization events. So they needed very accurate, very precise temperature control. And as you'll see, they wanted to image at very high resolution, so they wanted something that wasn't moving around a whole lot as they were heating it up. And then they also wanted to ensure that no matter where they were imaging, they could be very confident that the temperature was the exact same. So they needed a uniform heating membrane, one that was accurate, and one that was precise. And they also wanted to go to pretty high temperatures. This is showing the thermal uniformities. This is an SEM showing how our sample is melting across uniformly no matter where you're at. And this is kind of hard to see with this screen, but this is just at atomic resolution showing from 500 to 600 the sort of thermal drift you can expect. So very, very low. All right, so moving on to the actual science. What they were able to do pretty easily, and we have folks do this pretty routinely now, is heat the sample up and witness some phase transformations. You will get to see a demo of this later today, not a specific sample, but something similar to this. But as you heat these glassy nanowires, you can see in just the diffraction pattern that they start in an amorphous state, so you have the rings that you would expect. And with the spontaneous onset of crystallization, you're seeing diffractive peaks. And then as you heat the nanowire up even higher, you're actually melting it, right? So you go back into an amorphous state. So you have access to imaging. This is dark field imaging, but you also have access to diffraction, so you can characterize it in either way. So what they were interested in studying in this first paper, which was in Nature Communications, was just characterizing the temperature at which this occurred as a function of the diameter of the nanowire. So as you all probably know, as often the case in nanocrystalline or narrow-sized materials, there's a trend that moves one direction as the size of the feature length gets smaller, then it tends to reverse as you get to very, very small feature lengths. And they actually see the same thing here. So as the nanowires get smaller and smaller and smaller, they become more and more thermally unstable, forming this crystalline phase at lower and lower temperatures. But then the trend actually reverses. And so they were able to characterize this, again, using accurate temperature control to measure when this temperature, this phase transformation occurred. One of the interesting things, and actually this is kind of a compilation of two papers here, is on the top they were actually able to find a single nanowire that had two different size feature lengths. And what you can witness is the phase transformation occurring throughout the nanowire, and they're actually slowing down of the crystallization front in the neck region. That is a physical manifestation of the interplay between the thermodynamics and kinetics that are stabilizing, otherwise changing the onset of this crystallization temperature. And it's pretty cool to actually see that in a single system to see the balance of these two. They also did a follow-up study where they wanted to look at the crystallization rate as a function of cooling versus heating. So you can either heat up and crystallize, or you can cool down from molten state and then crystallize if you look at the TTT diagram. And what they show here is the exact same nanowire that has very, very different crystallization rates based on how they process the nanowire. I like showing that because that's a preface to seeing this process actually occur layer by layer, atom by atom, at high resolution. So this is kind of one of the upper echelons of the things that you can do with our system. You're really not limited by the system and your ability to resolve very small things. You're most likely limited by the microscope. So if you have a really good microscope, like Titan, for example, then you can do this type of imaging in your lab. So that's kind of the first study. I do kind of want to pivot a little bit and mention something that was not the case up until a few months ago, which is that we just launched an update to the system that I've showed here. We call it Fusion Select because you can get the system and you can sort of select whatever you want. So the system starts at just a single tilt heating system. That's what we're working with Kelvin on. But if you want to add to that double tilt, if you want to add to that electrical biasing, you can do that at any time. You can do that at time of purchase. It's all very straightforward. There's a lot of features sort of packed away to the system, which I'm not going to talk about in too much detail. But I do have some literature. You can learn more on our website if you want to know about the specific nuanced specifications that discriminate this from the predecessors that I've shown so far. One of the things that we worked really hard on with the system is to make sure that we were servicing the market and the growing need for electrical characterization in situ. So in this particular application, which is the field of memory devices, they're interested in studying the growth of these next generation resistive access memory devices in situ. So understanding how the read-write process occurs at the nanoscale to better understand how to optimize that process and make better, faster memory that has high energy density, high energy storage, but also is non-volatile, so it can switch back and forth. So anyways, these are a new class of memory devices that are really, really promising for a lot of different things. But the way that the switching occurs is by the growth of a conductive filament across a dielectric medium. It's that filament growth that stores the data, but that's also not very well understood. So in order to drive that process in situ, they wanted to characterize the switching mechanism. But one of the challenges of this was they needed to do it in a site-specific manner, right? So if you're studying an electrical device like a FinFET, or if you're studying some sort of very specific transistor, you need to know exactly where you are, which almost always requires FIB prep or something similar to that. So in this particular case, they needed to have a bulk device. They wanted to do a FIB lift out of a particular area, and they wanted to study that electrically. So that's a real big challenge because sample prep is always difficult. We actually worked with these customers to create an entirely new set of products called FIB-optimized electrical chips, which I'll go through here in a second. This is just an overview showing how the electrical biasing occurs in situ. Okay, so if you've ever done FIB, you know that it's not the easiest thing, and that's even more complicating in a lot of cases if you're trying to do additional characterization in situ. And so we worked with them to develop a whole series of FIB-optimized chips. These are FIB-optimized because they're almost identical to the FIB prep that you're used to if you're doing something on like a copper half grid. You're selecting your lamella and you're landing it directly onto our chip. Instead of a copper half grid, we have a silicon half chip. And by virtue of the platinum deposition or you're securing metal, you now have access to electrical control across your sample. You can also do final thinning directly on the chip, which means you can get atomic resolution as good as you would expect depending on the FIB operator. So this reduced the sample prep time by a factor of 3 or 4. And increase the success rate by a factor of 3 or 4 as well. So much higher throughput if you're doing electrical biasing in situ. Now, once they were attached to the sample, they could sort of cut preferentially through the different layers. So they could bias a single transistor, and this is what they're seeing in situ. So at the top, you can see the final device then to electron transparency. And on the bottom, I'm showing an EDS map, but just at the top, before I go into the actual result here, what they did is they characterized the sample and they went through the different cycles of forming one of these conductive filaments. So what they saw is what they expected, which is the forming, the set, and the reset phases. That's the common sort of hysteresis loop you would expect with one of these devices. But they also correlated that with ex situ measurements sort of on the wafer itself. And what they saw was, which is really important, is a very good agreement between the two data sets. Because at the end of the day, what you're doing in the microscope should be correlated or somewhat analogous to what you're expecting in the real world. And so characterizing them ex situ and in situ, they saw really good agreement, which made us really happy because that's exactly what we would expect to see. So then just kind of at the end of the study, they just wanted to see how the elements were segregating in the material in one of these multiple layers. And so they actually just cranked the current up and pushed the device all the way to failure. And what you're seeing here is the segregation of the chemical layers, the elemental segregation of these different layers across the device. So for example, what they saw is oxygen bridging the two layers, and then you can see, I think it's, titanium is pretty uniformly segregated into the layer that they were studying. So just characterizing sort of before and after EDS. You can do this in situ if you want, depending on the EDS system that you have. But yeah, this is sort of a full beginning to end process of characterizing this electrical device. Okay, so in the interest of time, I've only picked 2 applications to talk about, because 2 that I thought might be interesting. But I always like pointing out that this is not at all comprehensive, and it is by no means exhaustive of all the things that you can do with our system. So a few things that I'm hoping that you guys can take away. We're firm believers that you need to have uniform, accurate heating so that you know the temperature your sample's at, and that it's the same everywhere you're at regardless of whether you're imaging. If you're doing electrical biasing, having FIB optimized chips is going to help you out a lot. But also, there's a lot of features in our chips that I haven't talked about. But we work really hard to make sure that they're low leakage so that you don't have extraneous electrical noise that's otherwise inhibiting your ability to characterize your sample. And then we're also really big advocates for field support, having application scientists, and then products that are proven in the field. So this system has been tested by hundreds of labs around the world, and so we're confident in its ability to perform, regardless of the application of interest. The last thing I want to point out, just because I think it's really cool, is at the top left, this was a data set from actually a customer of ours in Prague. So we were starting to do a lot more customer interactive events, training, user group meetings. And this top result was actually pretty new. This was in an TEM. They were studying catalyzed nanowire growth. The reason I want to point it out is because when we saw some of these results and our customers saw it, they were pretty, their minds were blown. So this is the kind of thing that's at the cutting edge of in situ today. So this is a nanowire growing atom by atom, layer by layer, catalyzed the nanowire, and actually this process is driven by thermal control of the sample. So very rarely is it that people need to study samples at this unprecedented resolution, but this stuff is being pretty routinely done by some of the leading labs throughout the world. And I also think it's just pretty incredible because I really didn't believe it when I saw it, and everyone in the room sort of just had their jaws drop because we saw it was a 45-minute presentation of this stuff over and over again. So anyways, some really cool things people are doing with Fusion. Okay, so moving on, now I'm going to kind of pivot a little bit and talk about our liquid cell. So we call it Poseidon Select. Again, similar to our Fusion Select, you can get the system in whether you want to do electrochemistry or liquid heating. You can do that at the time of purchase, or you can upgrade later on. We make that whole process very seamless and easy. But with our Poseidon Select, what you're doing is studying materials in the liquid environment. So as it turns out, a lot of things on Earth are wet in some way, and so studying things in the liquid environment tends to be relevant for not only very, very wet things like colloids and liquid chemistry, living cells and stuff like that, but also for things like corrosion and just otherwise characterizing material in a realistic or active environment. You can do liquid heating, so you can heat a liquid up to 100 degrees, or you can do electrochemistry. But before I get into too much about what you can